Hello everyone. In this session, we are going to discuss about hydrostatic forces on vertically immersed surfaces. Of course, we have done this earlier, but here additional things like gravity dams and then log gates, etc., are vertical faced tanks. If they are carrying some liquid in it, how much is the force that will be coming on those faces, right? That kind of problems we are going to see, not that fully submerged surfaces. We'll see, we'll discuss so that you will understand what we are going to do. So here I have shown a vertical wall you can understand here. The height is h, the length in plan is b. You can say that it is the length. B it is called width, right? But actually the width is this. There is a wall, right? Now suppose this surface area, which is b into h, you know that the surface area of the wall is now the width b multiplied by h. B into h is acted upon by some pressure uniformly. This is P, the pressure, right? In such case, what happens is the force, the total force which is acting on the surface would be the pressure multiplied by the area. You have studied that pressure is nothing but intensity of the force or force per unit area. So force per unit area multiplied by B into H gives you the total force, right? But every time we will not be able to draw the figure like this. So what we do is this side view is generally drawn like this in the second figure, whatever I have shown. So vertical wall, maybe a single line or a double line wall is shown, and this pressure intensity is shown like that, right? So whenever a pressure diagram is drawn like this is called pressure diagram, right? In this particular case, pressure is not changing along the height. I have shown that it is uniformly acting because of some action. Let us say it is uniformly acting. Okay. Now the pressure intensity is measured in kilonewton per meter square, newton per meter square, something like that, right? But always it is force divided by area, and this diagram is called pressure diagram. Right? So these are the nomenclatures we are going to use often next. Okay. So as told here, the pressure is uniform or constant. Intensity of pressure is not changing. Suppose if it is 10 kilonewton per meter square, so everywhere it is 10 kilonewton per meter square. Okay. So it is constant without any variation. And let us say this length or this width is 5 meters and then height is 10 meters. 5 into 10 would be the area, that is 15 meters square would be the area. 50 meters square multiplied by pressure intensity gives you the total force which will be acting on the wall. Okay. So total force equal to pressure multiplied by area. So pressure is P, the area is B into H. That's why total force is P into BH. Okay. Now the point of application will be centroid of the pressure diagram. Okay. You have found the magnitude of the force. The total force is PBH. But where it will be acting? It will be acting at the centroid of the pressure diagram. If you know in elements of civil engineering, applied mechanics, if you remember, I'll try to show it here. If there is a UDL, we say UDL, right? Now intensity of pressure is so much, and then let us say something like 3 meters is the length on which the pressure is acting, load is acting, and load intensity is set, say for example it is 10 kilonewton or newton, let's say it is 10, please understand that 10 newton per meter length, let us say, is the loading intensity. Now we replace this by a single force. Now how much is that? 10 Newton per meter length for 3 meters. So it becomes 30 newtons. Where it will be acting? It will be acting at the centroid of the loading diagram, right? So the same loading is generally shown as a rectangular load, like that. So this will be acting vertical. So everywhere the intensity of the loading is same as 10 Newton per meter length. So like that it is. So when it is 10 Newton per meter length, and then if it is acting for 3 meters, obviously 30 Newton would be the load. Now you want to replace this by a single force. A single force would be 30 newtons. Where it will be acting? It will be acting at the centroid of the loading diagram. That is, centroid of a rectangle is midpoint. But if you take a triangular load, if you remember, if the pressure intensity is changing, then the things will be slightly different, right? Of course, this statement, that is the total force will be equal to pressure multiplied by area of what? Area of pressure diagram, holds good for this also. And then where it will be acting? It will be acting at the centroid of the loading diagram. It will be, suppose if it is 3 meters here, it will be 3 by 3, or this will be 1 meter, where that total resultant force will be acting. How much will be this force? This force will be equal to intensity of the pressure, intensity of the load multiplied by the area. The same statement holds good. Okay. Now in this case, because there is a face which is vertical and horizontal pressure is acting, where it will be acting? It will be acting at the centroid of the loading diagram. Where it will be? It will be obviously at h by 2 from the top or h by 2 from the bottom, where this total force will be acting. How much will be the force? That is given here. Total force is equal to P into BH. Okay. So this is when pressure is uniform. Okay. Okay, here there is a different case. The first case was simple, where pressure was uniform. Because of that, we have seen all this. Now suppose the pressure is changing from 0 to something like gamma h, because in fluids, as you go down, the pressure will be increasing at the rate of gamma. You know that now, right? So if you imagine that this whole thing is inside a liquid, right? Let me show the liquid surface like that. So here there is a surface of liquid with gamma as the specific weight of the liquid. Then if you move through a depth of z, the pressure intensity at this point will be equal to P is equal to gamma z. And then if you move whole height h, the bottom pressure will be equal to P equal to gamma into h. You know that at any depth h, the pressure will be P equal to gamma h. But when it is acting on a particular surface, it will be always perpendicular to the surface. That's why I have shown all the arrows horizontally, because the surface is vertical. Okay, so like this, the pressure intensity changing. Here it is, in earlier case it is uniform, but here it is changing, and then everywhere it will be there. I have shown only at 3 places, but everywhere, all this area B into H, this whole area will be acted upon by the triangular kind of pressure distribution. Okay. Now if you want to find out the total force on this, how will you find? Total force will be equal to the pressure multiplied by area. Fine. But pressure is not uniform. It is changing from 0 to gamma h or P. So 0 plus gamma h by 2, that will be average pressure. So this particular thing is nothing but average pressure, right? I have considered P let us say P at the bottom, or P dashed, if I call it as, this is P dashed. Okay, so P dashed plus 0 at the top divided by 2 gives you the average pressure. The average pressure multiplied by the whole area BH gives you the total force which will be acting, right? So the conclusion is hydrostatic pressure distribution is always linearly varying as triangular diagram. Okay, so that is how the pressure is changing in case of fluids. So this is not the case of fluid, right? So this is the case of fluid. So how the pressure will be changing? It will be changing linearly. It is a straight line variation, but it will be at some angle. This is also linear, but thing is it is constant, but it is continuously increasing in the case of fluids. Okay, the intensity of pressure is given in kilonewton per meter square, and okay, here I have the same diagram is shown once again in a separate way, right? Here what I have considered is this B. I have considered the length of the wall. This will be running for so many meters or so many kilometers sometimes, right? So this wall I have considered, for the sake of analysis, I have considered B equal to 1. This is an important part here. So 1 meter, and h is the height. So how much is the area which is exposed to the pressure? Obviously it will be h into 1, right? Now if you look at the area here, B into h, but B is equal to 1, right? Now how much is the pressure here? Pressure will be equal to average pressure, right? So average pressure will be the P at the bottom, the 0 at the top. So P plus 0 by 2, that P by 2, the average pressure will be acting. So P by 2 multiplied by B into H. But P is given by gamma into H, because gamma is the specific weight of the liquid, right? Of course, you have to assume that we have liquid standing like that with the surface at the top here, right? All this this whole thing is surface of the liquid which will be standing, and the unit weight or specific weight of the liquid is gamma. So obviously when you are at a depth of h, gamma h is acting. Because the surface is vertical, this will be horizontal. Okay, now P I substituted as gamma h, so it becomes gamma h by 2 into 1 meter length of the wall. I have considered 1 into h, so this becomes gamma h squared by 2. Now the total force has become gamma h squared by 2, but look at the pressure diagram. I have drawn the same thing as a pressure diagram here, right? H is the height, bottom is P is equal to gamma into h. Now if you calculate the area of this triangle, how much is this area? Area we calculate how? Half base into height, half gamma h into h, that is to say gamma h squared by 2. So interestingly, the total force per unit length, you can just observe there, the total force per unit length, I have considered 1, per unit length is simply equal to area of the pressure diagram. That is what is the major conclusion that we have understood from this slide. Conclusion is hydrostatic pressure distribution is always linearly varying as a triangular diagram. In addition to that, the total force per unit length is given by pressure diagram or area of the pressure diagram. That is a major conclusion. Okay. Next, pressure intensity is that way. That is area of the pressure diagram, gamma h squared by 2. Okay, that triangle is referred to as a pressure diagram. Now the point of application will be centroid of the pressure diagram. Where is the centroid for the triangle? What is the direction of the force? You know that the direction of the force is horizontally leftwards. Because of that, the total force will also be acting horizontally leftwards. It is a resultant force. So if I try to draw replacing single resultant force, it will be this way. Okay, this way. So this force, if I call it as capital F, right, that total force is acting here. Capital F is acting there, right? Where it will be acting? It will be acting at the centroid of the loading diagram or centroid of the pressure diagram. Now where is the centroid? Obviously it will be at a distance of h by 3 from the bottom. You know the centroidal distance for a triangle of a height h, it will be h by 3 from the bottom. So that is the position where the resultant force will be acting. Okay. Now there is one more case where, excuse me, the water is standing here at this level. Okay, the water surface is there. Okay, water or any liquid having unit weight gamma, but the surface which is immersed is slightly below. It is the immersed surface is over here, right? In that case, what happens is actually the pressure which will be acting on the top of this will be, say, P1, which is at a depth of H1, will be equal to P1 equal to gamma into H1. Now at the bottom, P2 will be because of the standing water of H1 plus H2, so gamma into H1 plus H2. So what is the pressure diagram which will be acting on the wall? It will be like this, which is for a height of H2, and it is starting with a value of P1, which is gamma H1, and then goes up to value of P2 equal to gamma of H1 plus H2. So it will be a trapezoidal pressure diagram if the surface is completely inside below some level. Here you can apply your earlier conclusions, means earlier knowledge that you are carrying, the force per on exposed or immersed surface. The same thing can be used here, but special case would be when the surface exposed surface is starting from the free surface. Okay, now here also one more thing that you should note down is if the length of the wall is becoming 1 per unit length, in such case area of the pressure diagram gives you the force per meter length. That conclusion is true even now. This force per unit length of the side wall will be equal to area of the pressure diagram. This conclusion is true even in this case. That's why total force per unit length of the side wall is equal to average pressure multiplied by the area. Okay. Now, what is average pressure? P1 plus P2 by 2 would be average pressure. Area would be, how much is the area? This length perpendicular to the paper, perpendicular to the screen is 1, because we are considering 1 meter length. So 1 multiplied by H2. So it becomes H2 only. So this is nothing but area of the trapezium also. You can just see here. How would you find the area of trapezium? It will be parallel sides summation divided by 2 multiplied by the distance between them. So that is what is becoming over here. So it is area of pressure diagram once again. So you should keep in mind that total force per unit length of the vertical wall is given by simply area of the pressure diagram. Conclusion is hydrostatic pressure distribution is always linear, varying as trapezoidal diagram here, because it is the top edge is slightly below the surface, free surface. If it is starting from the free surface, it would have been triangular. If it is at some depth, obviously it will be like that if the surface is vertical. Okay. So that is the area of the pressure diagram. So the point of application will be again centroid of the pressure diagram. You should find out the centroid of this pressure diagram. If you know the direct formula, it's well and good. Otherwise, break this trapezium into two parts. You treat this one rectangle, another one triangle, of which you know the centroids. Easily one can work out. Okay. While solving numerical problems, we will see how to handle that situation also. Okay. Okay. Here there is one problem I have considered. Simple problem. A plate immersed in water with edge AB at the free surface. Okay. Here the vertical surface is here, but when you see it from the end like that, the plate is ABCD, and then the length over here, perpendicular length, is 1.5 and height is 5 meters. Now if I try to draw pressure diagram for this, there is a standing water at the top. Obviously, just now we have seen that the pressure diagram will be a triangular variation, and then at any depth Z, it will be gamma into Z. Because there is a H right up to the bottom, the pressure will be P is equal to gamma into H. Now let us consider the gamma as 10 kilonewton per meter cube. So gamma into H becomes, so 10 into 5, that is 50. Moreover, kilonewton per meter cube multiplied by meter becomes kilonewton per meter square. So the pressure intensity at the bottom will be 50 kilonewton per meter square. So this is this length, right, side of the triangle will be 50 kilonewton per meter square. Okay. Now force per meter length of the wall we have studied is equal to area of the pressure diagram. So area of pressure diagram, how will you calculate? It is a triangle. So half, base is 50 kilonewton per meter square into height is 5 meters. So this becomes 50 into 5, 250 divided by 2, that is 125. Units wise, if you look at, it will be kilonewton per meter length. Yes, it is, because it is force per meter length of the wall. It is 125 kilonewton per meter length. The point of application of this force will be the centroid of the pressure diagram. Where is centroid? Centroid will be, for triangle, it will be h by 3 from the base. Now it is force per meter length, but what is the length of the wall? Length of the free surface, front surface is 1.5 meters. If I want the total force which is acting on the whole plate, I have to multiply by 1.5, because what I have calculated as 125 is only for 1 meter. So total force on the plate becomes 125 kilonewton per meter length multiplied by 1.5, that is 190.5 kilonewton. Okay. We'll go for the next problem. Okay, I have shown that it is actually being seen this way, but actual plate is different. Sorry. So that is the triangular distribution of the pressure. So what you should know is force per meter length of the wall is area of the pressure diagram, and the point of application will be centroid of the pressure diagram. That is the things to be taken from this particular slide. Okay, here the wall is below the free surface, and it is starting at this point and is 1.2 meters width, 3 meter depth. I don't know. Yes, I have shown it that way. You can just see that. That is the plate I am talking about. Yeah, that is the plate. You can just see that. Width of the plate is 1.2, 3 meters is the height. But when I see it edgewise, it is standing like that. There is water standing from the top only, right? It is not from here, but the thing which will be acting on this will be from this end, right? So how the pressure changes? The pressure will be changing right from the top. When it comes at this level, the depth is h1. So the pressure becomes gamma into h1. Here gamma is also in this also gamma I have taken it as 10 kilonewton per meter cube into 1 becomes gamma h1 becomes 10 kilonewton per meter square. That will be the pressure intensity there, right? At the bottom it becomes this plus additional pressure gamma h2 is 3 meters, so it is 30, or you can work out it as gamma into h1 plus h2. Gamma is 10 and the total height is 3 plus 1 4 meters, so because of that it will be 40 kilonewton per meter square at the bottom. Okay, now force on the plate, if you want, what we should do, see, though the hydrostatic pressure is A, B, C, D, E, A, right? Acting on the plate is only E, B, C, D. The plate is sensing only this part. Hydrostatic pressure from the free surface is a triangular distribution, but the one which is acting on the plate is only this part, which is a trapezoidal part, E, B, C, D. So therefore, force per meter length of the plate, if you want, it will be area EBCF. You can just see EBCF plus area EFD, that triangular. So I have, rather than directly calculating trapezoidal area, I have broken it into a rectangle and a triangle, so that it will be easy for me to calculate. So the one which is acting at this rectangle is designated as P1. The resultant, because of this triangular portion, I have called it as P2. Okay, P1 plus P2. Now how much is P1? It is nothing but area of this pressure diagram, which is 10 multiplied by 3. 10 into 3, that is 30, right? 10 is kilonewton per meter square, but multiplied by 3 meters becomes 30 kilonewton. So this is the kilonewton, right? 30 kilonewton per meter length plus area of the triangular portion, this triangular portion, that will be half base into height. Base is for this it is 30 into 3 divided by 2, so that becomes, I think, 45. This is 30, so it becomes 75. So this is 75 kilonewton per meter length. This is force per meter length. But how much is the plate length? It is 1.2. So what is to be done? Okay, here I have explained. P1 acts at the centroid of EBCF. P1 is because of this rectangular portion of the pressure distribution diagram. So EBCF. So P1 acts at the centroid of the EBCF. P2 acts as centroid of EFD. EFD is this triangular portion. So centroid of that, there it will be acting as shown in the figure. Now centroid for this rectangle would be at a height of 3 by 2. Of course from the top also it is 3 by 2. It is 1.5 meter. I have called it as Y1. The P1 acts at a distance of Y1 from the base. The P2 acts at the centroid of the triangle, which is at h by 3. Now here height is 3 by 3, that is 1 meter. So I have called it as Y2. Okay. Now to find position of resultant force P, the P is total force, which is 75 kilonewtons from the bottom. I use again Verignon's theorem, which states that moment of the resultant is equal to moment of sum of moments of all the forces. The same thing is used here. You can just see here this P into Y bar. Y bar is the point where that resultant force will be acting, right? P into Y bar will be equal to P1 into Y1 plus P2 into Y2. That is the moment. Okay. So now if you calculate Y bar, it comes out to be 1.2 meters from the bottom. So the total force on the plate is 75 kilonewton per meter length multiplied by 1.2 because it is per meter length. Now it will be 1.2 multiplied, because of that it becomes 90 kilonewton. Okay. Now where it will be acting? Okay, I'll try to show it. It will be acting at 1.2 meter from the base. So somewhere there in between, so that is the position where this total force P will be acting. The distance from the base, this to this, is nothing but this distance, 1.2 meters. Okay, so that is the analysis for submerged vertical surface. Okay, here there is a problem. You can read it, and then afterwards we'll try to draw the diagram for that. A tank 1.5 meter by 1.5 meter is filled with water up to 0.5 meter height, and remaining is filled with an oil of specific gravity 0.8. Okay, now if I okay, you can practice it. 1.5 meter by 1.5 meter is the size, right? The top plan size, and water is standing for 0.5 meter, and then remaining height for remaining is filled with an oil of specific gravity 0.8. Now which is on the top, which is on the bottom? Oil is there, water is there. Oil has got specific gravity 0.8, the water has got specific gravity 1. Because of that, so because specific gravity of the oil is less, it will be floating on top of water. Okay, so accordingly the diagram has to be drawn. Then afterwards it is said, determine the total pressure force on one side of the tank. Okay, okay. So here I have drawn the pressure diagram. It is said that 0.5 meter is the height of the water and 1 meter is the standing oil. Okay, so here there is oil, here there is a water. Now pressure diagram, if you try to draw, you can just have a look. That's important. First one is hydrostatic pressure diagram. This base will be equal to gamma into H, S into gamma W into H. Gamma is given by S into gamma, right? So here it is the top surface is nothing but oil. So specific gravity is 0.8 multiplied by 9.8, that becomes gamma, and the height H becomes 1, so it becomes 7.85. Of course the units would be kilonewton per meter square. Okay, now there is water here. This additional pressure diagram here, this particular pressure intensity is shown here. Again it is gamma into H, but here it is water itself, because of that directly written as gamma W. The H is 0.5, so 9.81 into 0.5, 4.91. Of course units are kilonewton per meter square. Now I'll calculate force per meter length of the wall. So force per meter length of the wall, if you want to calculate, we have to calculate area of the pressure diagram, F1. I have indicated it as F1. So F1 will be equal to half of 7.85 into 1, 3.924 kilonewton, which acts at, where it acts, if I take the bottom as the, top is taken as the reference, So from the top, if you want, this distance will be 2/3 of 1. So at 2/3 of 1 will be equal to 0.667 meters. 2/3 of 1 is 0.667 meters from the top. That is F1. Now this rectangular portion is also acting. I have called it as F2. F2 will be equal to this one, which is 7.85 into 0.5. That's also 3.924 kilonewton. Acts at, from the top, if we want, it will be 1 plus half of 0.5. I have made a mistake here. So this should be 1, right? This is 1 plus 0.5 by 2, so it becomes 1.25. Okay, F3 will be this, which will be half of 4.91 into 0.5 by 2, that is 1.226 kilonewton, which acts at, where it acts? It acts at the centroid. The centroid is again 2/3 from the top. So 1 plus 2/3 of 0.5, and if you calculate 1.333 meters from the top. So total force per meter length of the wall will be 9.074. It is summation of all this, right? Okay, 9.074 kilonewton. Obviously, this is per meter length of the wall. I have written it here, per meter length of the wall. Y bar, the resultant force position I have calculated. So Y bar will be equal to F1, Y1, F2, Y2 and so on. So that calculation you can do. Only thing is here there is a mistake, that this should have been 1.25. So we'll be getting some value of Y bar, and that is from the top. Okay. Now force on one side of the wall. This is to be understood properly, right? So this is important part. Force on one side of the wall. The side of the tank is 1.5 meter, because the tank is having something like that. Let's say, and you can imagine this is a tank. This length is 1.5. Now what I have calculated here, it is force per meter length of the wall. If I want on one side 1.5 meter, so I have to multiply by 1.5 meter, so that it becomes 13.6 kilometer. That is what is the additional important information that you should know. Thank you. We will stop here.